All right, so obviously we are in the same class, Introduction to Statistics, and we are still talking about the same thing, which is descriptive statistics. Descriptive statistics covers like half of all the statistics. Well, let me not say half. Descriptive statistics covers a third of statistics, right? The first third of statistics is data collection, sampling, right? That's the first third of statistics. How do you actually collect data? How do you understand data? The second third of statistics is descriptive statistics. And then the last third of statistics is inferential statistics. Now, this week, we're going to specifically be looking at relative standing in z-scores, and in particular, how we can measure relative standing in z-scores. So, just our pace checker. Where are we? What have we done so far? So far, we've collected data. And now what, right? That's where we were. We collected data. We're in the now what section. What do we do now? What comes next? So again, what are the important characteristics of data? There were 5 of them. What are those 5 important characteristics of data? Anybody? Come on, mute. Sam? We had
center, variation, distribution, outliers, time.
Very good. We had C, V, D, O, T. Right? Those are our important characteristics of data. Now we have talked about center a lot, right? We've talked about center a lot. We've talked about variation. That was our why did my mind just go blank? We talked about variation as range, standard deviation, IQR, right? Variance. So we talked about variation. We talked about the shape of the distribution. We haven't really talked about outliers yet. Like, we've mentioned them, but we haven't really gone into how you can actually tell if something is an outlier, right? In time, we're going to come back to time. Like time, we always just are in the process of coming back to time. Because it's sometimes present, sometimes it's not present, but it's not much for us to talk about. What we talk about today will be under variation, right? And in particular, we're looking at, again, relative standing, right? And that's under variation. So just giving you orientation for where we are and what it is that we're trying to do now. So basically, with relative standing, can someone read the first little bullet point?
We want to sort and compare data.
Yep. So that's kind of what we're trying to do. We've collected all this data, and now we need a way to sort it, right? Like, you know how you look at a list and you're like, oh, I'm trying to understand this list a little better. And so what's the first thing that you do? If you get a list of names, what's one of the first things you do with your list of names? Put it in what order?
Alphabetical.
Put it in alphabetical order, because sorting the data, right? Sorting that list helps our brains process it, right? The same thing is, it is the same thing when we get numerical data or any other kind of data. We want to put it in some kind of order. Unfortunately, we can't just click sort and put it in alphabetical order. There are other ways that we can actually sort the data, and the other part is alphabetical order is not really all that meaningful, right? We want to put it in a meaningful order. So that's what we're trying to do here. Sort and compare the data in a meaningful way. Can somebody read the next one?
Power stream are different individual data values.
So let's say you went to a random island, right? Let's say you crash landed on a random island, right? And, better yet, let's not say an island. Let's say you're an astronaut. Your spaceship gets lost in space. You end up on a planet. You see an alien come up to you. This alien is like 8 feet tall. Is that alien tall for an alien or short for an alien? That's the question. Is this a tall alien? We just came across an 8-foot tall alien. Is this alien tall or is this alien short?
Compared to the human race, he's tall.
But we're not comparing to. We're saying tall or short for an alien.
Well, we wouldn't be able to compare him to his
Another
species
alien.
unless we see some other aliens.
Exactly, right? That's where that word relative comes in, right? Because we're looking at relative standing without being able to see all of these other aliens, or not even all of them. We don't need to see all of them. Without being able to see a large number of them, like a good enough representative sample of them, right? We don't know if this alien is tall or short. This alien might be a baby alien, and maybe the rest of the aliens are like 12, 13 feet tall, right? This alien might be a giant alien, and maybe all the rest of the aliens are like regular human size. Well, we don't know until we can compare them, right? So we couldn't say, is this alien extremely tall or extremely short, right? We can't tell how extreme that alien's height is, right? And that's one question that relative standing will let us answer. We'll be able to do some statistics to say whether or not, you know, our random alien that we bumped into is tall or short. And somebody read the next one.
Things closer to the center are less extreme, while things further away from the center are more extreme.
Exactly. So when we put everything in a line, in our order, we've already sorted this data. When we put it in a line in our order, if something is close to the middle, right, that means it's not so extreme. But as we get towards the edges, whether it's the far edge, right, going lower side, or the other upper edge going towards the higher side, that's when we get to the extreme values. So that's the reason why we wouldn't call someone, a human person, who was like 5'9", we wouldn't call them tall or short, would we? Because 5'9" is about average. 5'9", 5'10", that's average. But if we saw, and what we mean when we say that's average, we mean this person's height, right, is like in the middle of a bunch of other people's heights, everyone else's heights. If we got a whole rack of people together, it's likely that this person's height will be in the middle. On the other hand, right, if we had someone who was 7 feet tall compared to other humans, they're not going to be in the middle of that line, are they? When we put all the people in the line, they're not going to be in the middle of the line. Where are they going to be? They're going to be somewhere towards the tall side of that line, right? Because they are relatively tall, or their height is more extreme because their height is further away from the center. And we had those different ways of measuring the center. Who can remind me, what were those different ways? We had three M's for measuring the center. What were those 3 M's?
Medium, and mode.
Mode.
Yes, mean, median, and mode. Right, so those are our 3 M's for measuring where the center is. Right, we can look at how far things are away from that center point. Somebody read the next one for me.
We also want to rank data values. What percent of data is smaller than a particular value? What percent of the data is larger than a particular value?
Exactly. So when we rank it, right, we want to know kind of where those percentages are. You know, what percent of people were, if you score on a test, you want to know what percent of the class scored higher than you, what percent of the class scored lower than you, right? If someone comes and tells you, you know, let me think, what kind of, if someone comes along and tells you something about your health, I'm trying to think of some health measurements, but a lot of health measurements are measured like that. But someone comes along and tells you your blood whatever level is this. Y'all are doctors? I'm not a doctor. I don't know what that means, right? The only way that has meaning is like, is this normal? That's where it gets meaning, right? Is it normal? And then the doctor may be like, well, it's the such and such percentile. You're in the such and such percentile, right? Meaning such and such amount of people have a value that's higher than yours. And I'm like, oh my God, 99% of people have a value that's higher than my value? That's not so good, right? Or if it's something in the other direction, it could be 99% of people have a value less than yours, right? And now I know that I'm really, really extreme. And can someone read the last bullet point that we have here?
We call the data point. Oh, go ahead.
We call the data point we are concerned with X.
Yes, so whatever data point, when we're talking about relative standing, usually we're talking about a single value, a single data point, and how it fits, how it rates relative to the other data points, right? And that single data value we're talking about, we call it X, right? So for example, let's say we were looking at Chanel's height, right? Or something like that. Chanel's height is X. We've collected everyone's height, but we're in particular concerned with Chanel's height. Her height becomes X. So we did have two.
Please, sir, I have a
Go ahead, Hermila.
before you pass. Yeah, on the third one, you said you used the word extreme, and I was a bit confused. Can you give me a synonym for this word and this reason, particular reason?
For extreme.
The things closer to center are less extreme. Can you give me another word for
extreme? Okay.
What you mean?
So let's say you ran into someone, right? Let's say you ran into a basketball player, right, Hamila? How would you describe that person's height?
How tall they are.
Yeah, but like, what would you say? Like, basketball players are really, really tall. And if I remember, Hamila, you're kind of on the short side, right? So this might be somebody who's like 3 feet taller than you, right? How would you, like, you look at their height and you'd be like, what? What would your exclamation be like? What would you say? Wow, this person is so tall. Like, what would you say? Would you say they're really, really tall?
Yeah, I guess taller. I can use taller than someone.
Yeah, right. So as we get taller and taller and taller, right? The taller and taller and taller we get, that's extreme, right? So now their height is really, really extreme. So like there's 6 feet, but then there's like 6'5", then there's like 6'6", then there's like 7 feet tall, then there's like 7'5". The taller we get, the more extreme we get, right? That's kind of what extreme is saying. How far away from what is average or what is normal is something. Does that make sense? Does that help?
Thank you.
All right.
Yeah, I did.
So again, we had two main measures of center, right? Two main measures of center. We did have the mode, but the mode sometimes gets left out. The two main measures of center that we had, that are kind of the ones that we usually will be using, those ones are the mean and the median. Those ones are the mean and the median. And because we have two different ways of measuring where the middle is, there are two different ways of measuring, there are multiple different ways or approaches of measuring how far things are away from that middle point, right? So again, just as a review, when we were looking at variation, we used the standard deviation to measure how far things were away from the mean, right? And this all talks about the standard deviation, but that's in what we did in, what was that, 2 weeks ago or last week? That's where that is, right? But this is just a review. How far things away from the mean? We use the standard deviation to tell us that. And some more information about the standard deviation, but you should have seen it already, right? And a little bit more, just so that when you do your review, you can have it right there for you to do the review right away. Right? So with the mean, we have a very particular way of measuring how far a specific data point. Remember we said when we're talking about a specific data value, right? We call it what? What do we call that particular data value? Is one of the things we made. What do we call it? Anybody remember? What do we call that particular data value?
X.
X.
Saying for the mean?
No, when we're talking about one particular data value, what do we call it? We call it X.
X.
Right? So when we're looking at measuring one particular data point's distance from the mean, again, the standard deviation was measuring like all of the data and how far all of the data is from the mean. When we're talking about measuring how far one particular data point is from the mean, right? We want to know exactly. So we had done something before in class where we were like a certain number of standard deviations. We were kind of getting exact with the number of standard deviations away. We were like 1 standard deviation, 2 standard deviations away. But we want to know like exactly how many standard deviations we are away from the mean. So like 1.5 standard deviations, like that kind of thing. 1.37 standard deviations away, like precisely how far away. And the way we do that, we use what we call z-scores. Right? And basically, z-scores are a measurement of exactly how many standard deviations one particular data point is away from the mean. That's what a z-score tells us. Exactly. If a z-score is negative, then that means our data point is less than the mean. And if a z-score is positive, then that means the data point is greater than the mean. Right? That's what the z-score tells us. And we have a formula. It looks a little complicated, but it's a very, very simple formula. Just trust me on that. It's simple. We're going to do some examples with it. It's a very simple formula. And these formulas are for 2 different scenarios. If we're calculating the z-score of a sample or if we're calculating the z-score of a population. Again, the main difference between these two is if we're calculating the z-score of a sample, we need to use the sample mean. On the other hand, if we're calculating a z-score of a population, we use the population mean. That's the only difference. The only difference is in the letter that we use to represent the mean. Right, so let's do an example, a z-score example. Let's actually look at what each letter means. So again, x is the data value, right? That's x, whatever data point that we're looking at. So let's say we measured the amount of money in everyone's bank accounts, and we wanted to say in particular, right, how much money did Danita have in particular, right, compared to everyone else's. And we want to find Danita's z-score, right, in particular, and see how far away from the mean her bank account value was. So x becomes how much money Danita has in her bank account. X bar, which is this, or mu, which is this, right? That's the sample mean or the population mean. And then S, or sigma, right, is the sample standard deviation or the population standard deviation. Right? So it's still the same kind of idea, right? We take the value, we subtract the mean, and we divide by the standard deviation. That's kind of all we're doing in both of them. Take the value, subtract the mean, divide by the standard deviation. It's a very simple process to do because it's just subtract and then divide. That's literally all you have to do. Subtract and then divide. Don't get confused by the fact that we're calculating each one with different symbols. They're both essentially the same idea. Take the value, subtract the mean, divide by the standard deviation. We can actually write that. So the z-score equals the value minus the mean divided by the standard deviation. Right, that's what we have. The z-score is the value minus the mean divided by the standard deviation. Right, both of them are saying the exact same thing. The only thing again that's changing is, are we talking about the population or are we talking about a sample? So before we go into some examples, right, a couple of important notes. When we find the z-score, we don't actually put units on it, right? We don't put units on it because it's telling us a number of standard deviations, right? And that aspect of it not having units is very important, and it'll become more apparent why it's so important later. Now, who remembers when we were talking about the standard deviation, how many standard deviations did you have to be greater than the mean for you to be significantly high? Like, how many arm lengths did we say you have to be?
Or 3.
So 3 was like a lot, but it was almost 3, not quite 3.
You talking about when you did the example about sitting at the bar stool?
Yeah.
So 2, was it the second one?
Exactly, it was 2. Yep.
Okay.
So it's significantly high, right? If we're 2 arm lengths, right, or 2 standard deviations or 2 bar stools away from the middle, it's significantly high. And as such, because the z-score is measuring the number of arm lengths or the number of standard deviations, right? If the z-score is bigger than 2, then it's that data value is significantly high. Because all the z-score is measuring, how many standard deviations away. So if the z-score is bigger than 2, then it's significantly high. Likewise, on the other side, if the z-score is less than -2, right? So the significantly high section is over here. Z-score is bigger than 2. And the significantly low section is back here. Z-score is less than -2. Right? So that's kind of our connection. It's a similar kind of thing, except now we have an actual way to calculate an exact number of standard deviations. Another important note: no matter what else you get, no matter what other round-off rules you have, when we find the z-score, we always round it off to 2 decimal places, right? For our z-score, it's always rounded to 2 decimal places every single time, no exceptions. So, for example, if you calculate the z-score and you just get 1, what should you write instead of 1? We need 2 decimal places every single time.
1.00.
Exactly. So instead of writing 1, we're going to instead write 1.00. Right? Instead of writing 1, we're going to write 1.00. And that part is very, very important. That we want to round it off to 2 decimal places every single time we find a z-score. I'm not going to be that professor who's like taking off points because y'all didn't round it to 2 decimal places, but I will start doing that if it gets egregious. You need to round the z-score off to 2 decimal places. Right? So if it gets egregious, I'll be like -1. You didn't round it to 2 decimal places. Right? And if we have a very, very large z-score, right, that's going to be a data value that's more extreme. Right? And again, that's just looking at the number, not the sign. And by that, so Hermila, I'll take it back to our height example. If I told you, Hermila, that somebody's height had a z-score of 5, right? What would you know about that person's height? Their height is going to be really, really extreme because their value in their z-score is putting them so far away from the mean, right? It's 5 standard deviations away from the mean. So it's going to be they're going to be really, really, really tall. Or their height will be extreme because they're so tall, they're so far away from the mean. They're 5 standard deviations bigger than the mean, so they're just all the way up there. On the other hand, if there was somebody who had a z-score and their height had a z-score of -3, they're going to be short because they're much less than the mean. So the larger the absolute value of the z-score is, right, that's the number without the sign, the further they are away from the mean. And the smaller the absolute value of the z-score is, the closer they're going to be to the mean. So question, who would be taller? A person with a height z-score of or a person with a height z-score, so I just put z1 and z2. Person 1's height has a z-score of 2.5, and person 2's height has a z-score of -1.9. Which person's taller? Is person 1 taller?
Z1.
Z1, that person would be taller because their z-score is higher, which puts them further away from the mean on the positive side. Z2 is going to be shorter because their z-score is telling us that they're shorter than the average height or shorter than the mean height and is pretty far away. It's almost significantly low. What about these 2 z-scores? Who would be let's say we were weighing baby elephants, right? We're weighing baby elephants, and the first baby elephant had a z-score, a weight z-score of 0.95. The second baby elephant had a weight z-score of 1.2, and the third baby elephant had a weight z-score of negative 0.5. So the question I have for you is, one, were there any elephant, like baby elephant weights that we should be like, oh, that's concerning? And the second question is, which baby elephant weighs the most? Which one weighs the least? So are there any of these baby elephants? These are all baby elephant weights. That's what these are. Baby elephant weights.
So Z2 would be the heaviest.
Okay, so that's a start. Z2 is the heaviest, and which one's the lightest?
Z3, because it's a negative.
Okay.
And that's the more concerning one, because that means the elephant is underweight.
Right.
Not necessarily. Not necessarily underweight. Because we have two words, right? They may be less than the mean, but they're not necessarily underweight, because the way we're going to define underweight or overweight is based on that significantly high, significantly low threshold. Right? So significantly high, that significant word means that this is cause for concern. So are there any elephants that fit in that category of significantly high or significantly low?
So 0.5 is significantly high, no? Right?
No. What does it have to be less than for it to be significantly low?
Smaller?
The mean.
No, not bigger than the mean. Somebody said it.
-2.
-2, exactly. So let's draw elephants on this little table here, right? So Z1 0.95, that's gonna be like right here. Z2, that's gonna be like 1.2, that's gonna be like right here. And then Z3 -0.5 is gonna be like right here. And we can see that none of these z-scores are in this range, are they? None of the z-scores are over here. None of the z-scores are over here. So none of them are significantly high or significantly low. They're just right there in the middle, and they're pretty normal. They're right there with just about everyone else. And it's not until we start getting past that point when we get to, I'll say, cause for concern or things that we should be worried about. These are normal values. These values are not significant. That's what we call them, actually. We say that those values are not significant. So if it's not significantly high or significantly low, then it's just not significant. All right? So what we're going to do really quickly, are we going to do this really quickly? We're going to do an example. I'm going to write some numbers down, and we're going to do an example with the numbers. So let's go back to our alien example. Right? We went to a planet, and when we got to the planet, right, we found these aliens. Please don't laugh at my alien drawing abilities. We found an alien. That's an alien. Oh, don't make that face, Chanel. So here's our alien. And when we ran across this one-eyed, these are mouths. That's what these are. There's one eye, 2 mouths, 3 fingers, and 1 foot. When we came across our alien, we're like, what in the world is going on here? And our alien here, right? Our alien had, let's do a different, so we always do height. I'm going to do a slightly different example because we always do height. I want to do a different example. Our alien, instead of height, we note that our alien only has 6 fingers. And so we are curious. Do all of these aliens only have 6 fingers? Is it some of these aliens that have 6 fingers? Right? Is this alien special? An alien is blue skin but is green on the inside. I'm adding a little bit extra. There you go. There's a blue-green alien. So that's the question. Do all aliens have 6 fingers? Or is our alien that we ran across special? Right? And how can we figure that out? What should we do to figure out if our alien is special or if all aliens have 6 fingers? Or if most aliens have 6 fingers? Anybody have any ideas? What can we do?
We need to find more aliens, don't we?
We need to find some more aliens. So that's a good idea. So we collect aliens. Now, unfortunately, because we don't know the terrain, we only have access to a limited number of aliens. So no matter what kind of sample we do, our sample is going to be what kind of sample? Because we only are going with the aliens that we have access to. So what kind of sample is that going to be? Starts with a C. We're finding. Go ahead, somebody. Wait. Somebody was gonna say it.
Was this control?
Nope. What kind of sample is this? It's an easy sample to find because we're only doing the aliens that we readily have access to. What kind of sample is this? It's an easy one. The sample. Say it one more time.
It's convenient.
Convenient sample, exactly. Right, we're doing a convenient sample because we're only doing the ones we have access to. But like I said, we ain't about to go exploring this alien planet because we don't know what these aliens are about. So we just are going to be able to sample the 15 aliens that we run into. Now, when we run into these 15 aliens, we find that the first alien has 6 fingers. That's our alien. The next alien has 6 fingers. The next alien has 7 fingers. We run into a 1-finger alien. We get a 9-finger alien, another 6-finger alien, an 8-finger alien, a 3-finger alien, hold on, not a 3, a 5-finger alien. How many is that? 1, 2, 3, 4, 5, 6, 7, 8. Let's see, we were doing 15. Another 6-finger alien, an 8-finger alien, a 7-finger alien, another 5-finger alien, a 6-finger alien, 9 fingers, 12 fingers, and I think that's 15. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So we got 15 aliens, right? And we counted how many fingers they have. Clearly, these aliens have a diverse number of fingers. Maybe for these aliens, fingers are like height and weight for us, where, you know, you couldn't really just say how tall or how much somebody's gonna weigh. It kind of varies. So all these aliens got different numbers of fingers, and we want to crunch some numbers and see, is our friend the 6-finger alien, and this is the 6-finger alien's name. Is our friend this 6-finger alien? This is his name. I don't know how to pronounce that, so we're just gonna leave it as that. I don't know how they pronounce that name. So is our alien with the 6 fingers, is this alien normal or is it odd? That's the question. So what can we do from here? So we've collected data. Now what?
We're going to find the mean and the median.
Okay, yes, but let's get...
We got to arrange it. We have to first arrange the numbers.
Arrange it. But there's a whole title for everything that is what you're describing. Yeah, but there's a whole... Like,
Sorted?
What's that category of statistics called? Starts with
you said
D.
earlier.
Yes, I did
What is
say
that
earlier.
with?
A D. We've been on this category for like the last 3 weeks.
Can we add all of them and then divide it by 15?
We could do that. That would be finding the mean, but we're trying to find out what category of what are we doing right now? How do we call everything that we're about to do right now?
Data.
Nope, DE.
No, descriptive.
There we go. We're going to do some descriptive statistics, right? Yeah. So, I don't know if y'all know this, but that's how we start class, isn't it? We've collected data, now what? Right? That's the question that you should always have burning in your head. What do we do now? We've collected this data. What do we do now? Because that's like the starting point for where you will always be. You will always be at a point where you have some data and you're trying to figure out, what in the world do I do? And what do you always start with? You always start with descriptive statistics. So yeah, we're going to arrange it, put it in order, visually represent it, all of that stuff. But for right now, because we kind of have a clear path, right, we want to find out how extreme our 6-finger friend is.
Normal.
Maybe not. We got to do some numbers, crunch some numbers and see. So we're going to start off and we're going to use what we know. So we know if we want to tell how extreme something is, what do we need to do? We need to find the z-score. So that's what we need to find. We need to find the z-score to be able to tell how extreme, right? How extreme the value is. We need to find the z-score. So to find the z-score, the question is, what do we need? What information do we need? Well, let's write down the z-score formula and see if that can help us. So our z-score formula is z equals, and for this one, because we have a sample, right, and not a population, we're working with a sample, the sample z-score formula. So we have x minus x bar divided by the standard deviation. We know what x is. What's x going to be in this example? What's x going to be?
6.
6, because that's the value that we are concerned with. Do we know what the mean is? No, we don't. We need to find the mean. Do we know what the standard deviation is? No, we don't. We need to find the standard deviation. So we need to find the mean, we need to find the standard deviation. Alright. So, let's do that. Let's start off with finding the mean. What is the mean for this sample that we found? What's the mean number of fingers that aliens have? What's the mean number of fingers that aliens have? How do we do that? Yeah, I said it before. How do we do it? Add up all the numbers.
Add up all the numbers and divide it by 15.
Exactly. So let's add them all up and divide by 15. I need multiple people to find the mean so that we can make sure we're doing it correctly. All right. So, did we get any answers? We have 6 plus 6 plus 7 plus 1 plus 9 plus 6 plus 8 plus 5 plus 6 plus 8 plus 7 plus 5 plus 6 plus 9 plus 12. I got 101 for that, and then divided by 15.
I got 6.73.
Okay, that's what I got as well. The mean is 6 point. Now we got 7.3, but again, remember our round off rules, right? When we look here, these have how many decimal points? How many decimal points do these ones have? They only have 0. They don't have any decimal points behind them. They don't have any decimals behind them, right? So there are no decimals behind them. So for our measure of center, we just keep 1 additional decimal point. So we're just going to put 6.7. That's what we're going to put, 6.7. So this is our mean. So now we have the mean. Now we need to find the standard deviation. Now I know I wasn't requiring you all to calculate the standard deviation out by hand. That's okay. We're going to go and use some technology to find our standard deviation. So let's do that. So I'm going to just make a little document in Excel. There we go. So I can get my numbers up here on the side. So we got 6. Let me see. Uh-oh. What did I just do? Undo. We got 6. Oh, I need my keyboard. I don't know why my keyboard's not popping up. 6. We got 6. We got. Can y'all read the numbers off for me, please? 7. 1. 9.
6.
8. 5. 6.
8. 7. 5. 6. 9. 12.
All right, so we got all our numbers there. Right, that's perfect. Now we can find the standard deviation by just going equals standard deviation, and it's the standard deviation of a sample, which is fine. I want to let me select it. There we go. And that's our standard deviation. Y'all can see that number?
Yes.
All right, so that's our standard deviation. So we got our standard deviation. We got 2.43, right? Or just 2.4 if we keep the one number after. So S equals 2.4. That's good. Now we can find our z-score. So let's find our z-score. That'll tell us exactly how many standard deviations we are away from the mean. So we're going to plug these numbers in. And when we plug these numbers in, what will we get? So we have z equals 6 minus, what's the mean? 6.7.
6.7.
Divided by the standard deviation that we just found, 2.4. And when we get out for our z-score, 6 minus 6.7, that equals minus 0.7, divided by 2.4, and we get minus 0.29. Now, what do we say about our z-score? We always want 2 decimal points. I'm just going to emphasize that by putting the 0 in the beginning. 0.29. And that is our alien's z-score. What does this z-score tell us? What does this z-score tell us? Does it tell us anything? What were we trying to find out?
That is not that extreme.
That is not that extreme. That is actually not extreme at all. It's almost like right in the middle, right? It's almost 0, which a z-score of 0 would be the mean itself, right? That's what a z-score of 0. What's the distance from the mean? There is no difference to the mean. That would be a z-score of 0. So is our alien, we'll just call our alien Paul. That's what we'll call our alien. I don't know how to pronounce. I can't pronounce this right here, so we'll just call our alien Paul. So this tells us, because our alien z-score was not significantly high or significantly low, our alien has a regular number of fingers. Hermelia, you have a question?
So when you went to the Excel to find out the standard deviation, after you put down the numbers, how did you get 2.4.
So when I went to Excel to find the standard deviation, right? I started typing in. So look up here. See stdev.s. That's what I started typing in. You just started typing in stdev, right? You'll see it come up. Even if we do stdev, that's fine. There's something wrong here. We just go undo. I started typing stuff. So once we start typing it in, this is the code. Just like how we had type equals mean, this is what you type in to get the standard deviation. Right, that's just what you type in. So I typed it in. I selected the correct data variable, the correct sections, and when I did that, this is what it gave me. Does that make sense, Amelia?
Yeah, it does. Thank you.
All right.
Is there another way to do it on our computers rather than on Excel?
I mean, you could do it in Google Sheets. The only other method that I could give you is, the only other method I could give you is just to learn how to do it by hand, which is not hard to do by hand. It's not very hard. The method for finding standard deviation by hand is in the slides, but it's not very hard to find a standard deviation by hand. And for a short list of numbers like this, it might even be quicker to find it by hand than going in Excel. But you use a tool like Google Sheets, or you use a tool like, use one of those tools. You might be able to do it with the Desmos calculator, but I'm not entirely sure. Yeah, I'm not entirely sure. But yeah.
Professor, Nikki, I have a quick question. I want to make sure at the end when you
just went on mute.
Okay. When you did the 0.29, because it was negative 29, so you added the decimal. You say you put the decimal. Two spaces to show
negative 0.29. That was the answer. When I did that in my calculator, I got negative 0.29. The only thing I put there was the 0. So I wrote negative 0.29 instead of writing it like this. I just put the 0 there. That's all.
Okay.
So it's the same number, but all I did was put the 0 there. Right. So what does this tell us? This tells us our alien is normal, right? Alien is very normal. There's nothing interesting about our alien having 6 fingers. Is there any alien here, based on their Z-score, that you think, or just based on looking at it, is there an alien here that you would be like, let's investigate this alien and see if this alien is weird or not? Which alien would we investigate?
12.
One with 12.
Okay, let's investigate the one with 12 fingers.
12.
Let's find that alien Z-score. So this was our 6-finger alien. Let's investigate our 12-finger alien. Let's investigate. We get Z equals, what is we going to put for X?
12.
12. That's the value we're concerned with now. So we do 12 minus what? What are we subtracting?
6.7.
6.7. The mean has not changed. And then we do divided by what?
15. 2.24.
2.4. The standard deviation hasn't changed. And what is this going to equal? Let's do the math. Use your calculators. Use your Desmos calculators on your phones or whatever if you don't have an actual calculator. What'd you all get? Anybody got an answer yet?
$2.20.
Remember your rounding. Make sure you're rounding correctly. 2.2 what?
2.21.
Exactly, because we had 2.208. So when we leave off that, when we just want to round at the 0, we need to round it up to 2.21. So what does that tell us about our 12-finger alien? Is our 12-finger alien normal? This is a Z-score.
No.
He way off.
Yeah, but what was the specific term that we had to reference a Z-score that's this high? We had a specific term. What was that specific term?
Extreme.
It was extreme, yes, but it's 2 words. What are the 2 words down here? What 2 words do we have?
Significantly high.
Significantly high.
Significantly high, right? This alien z-score was larger than 2. Thus, the alien's number of fingers is significantly high, right? Any other alien we can see here? What other alien do we
question.
See? Hold on, wait, we have a question? Go ahead, Chanel, what's your question?
So, I understand the 2 on both sides, but this is 2.21. So even though it's 2.21, that's still considered extreme?
It's bigger. Is it bigger than 2?
Yeah.
Okay, yeah. So it's still extreme. Like, Chanel, think about it like this way. It may seem like a little tiny bit, but if I had an option of giving you $2 million or $2.21 million, which one do you want?
I understand.
Okay. Yeah, you want that 2.21 million. You like, don't cut off my $0.21 million. And when we get further on, we'll use z-scores for other stuff. And it'll be a similar kind of thing where that 0.21 will make a big enough difference to like change numbers, significantly. So yeah, it's significantly high. Once we hit 2, anything past that is significantly high. And what I would even say is, you might even want to just take a look a little closer at any values that you have that are even closer to. Like if you get 1.95, don't be like, well, it's 1.95, it's less than 2, so we're good. No, I mean that's almost significantly high, right? And because all of these values are kind of arbitrary a little bit, right? Because they're all kind of arbitrary, you still want to, give some, like, look at it a little closer. Does that make sense? All right. What other value might we consider? Which other one might we consider?
One finger.
The one with 1 finger, right?
One.
I mean, yeah, and what you all did made total sense. We know what the middle is. The middle is about 6 or 7 fingers. That's in the middle, 6.7 fingers, which is about 7 fingers. I don't know if these aliens can have half of a finger or whatever, but it's 6.7 fingers that's in the middle. So we know which 2 are on the extreme sides. The alien with a whole bunch of fingers is number 12. The alien with not a lot of fingers is number 1. Right? So let's find the 1 finger z-score. What's the 1 finger alien z-score? How are we going to do that? What are we going to put for x?
1.
1. And we're going to do 1 minus what?
6.7.
6.7.
1 minus 6.7. And then we're going to divide it by
2.4.
the standard deviation, 2.4. And what do we get when we do this? Well, 1 minus 6.7, that's going to be minus 5.7.
So negative 2.37.
8. Negative 2.4.
Say it one more time, what y'all get?
Negative 2.37.
Almost, but don't forget your rounding. Negative 2.3 what?
3.8.
3.8, because we had 3.75, so we need to round up. That's 7. So is this alien's number of fingers extreme or not?
Would it be extremely low?
Yeah. Or what's the other word? Significantly low, right?
Significantly low.
Yeah, because look at that. That's less than negative 2. So this alien's number of fingers is significantly low. Now let me ask you something. If you run into a 5-finger alien, right, should you think that's normal or not?
Yeah.
Yeah.
I would think it's closer to average, yes.
It's close enough to average. That's normal enough. Mosquito that's been eating me in here. And I just tried to get it. I don't know if I got it or not, but it's been chewing me and eating me alive. But I'm sorry, y'all. So yeah, that would be, if we ran into a 5-finger alien, that would be pretty normal, right? All of these other aliens, their number of fingers look pretty normal. They look normal because they are less than 2 standard deviations away from the mean. Right? What if we ran into a 20-finger alien?
It would still be off. It's way off. It would be still extreme, significantly high.
Exactly, it would be significantly high. Right? So our alien that we ran into, Paul, was a pretty normal alien with a normal number of fingers. Now, Paul's number of feet, they're not so normal. Most of the aliens in Paul's community have 8 feet instead of 1 foot. But anyway, I digress. Let's go back. So we did an example where we found the C-score. Now the other thing that we need to talk about, which I actually think we're going to stop here. We're going to stop here, and we're going to pick up on the other side next week. That's what we're going to do. We're going to stop here and pick up on the other side next week. Go ahead, Ashley. You have a question?
Yeah.
Go ahead. What's your question, Ashley? I think I was hearing a question.
Oh, I'm sorry. I'm not even muted. I'm sorry.